All right, this audio video handout is about osmosis, and osmosis is the diffusion of water across the cell membrane. And all cells, any living cell is surrounded by a cell membrane. It's also called a plasma membrane, and those cell membranes in all animals, plants, bacteria, every living cell, those cell membranes are composed of phospholipid bilayers. And the phospholipid bilayer is semi-permeable, and that's because there is water on the inside. There's water on the outside, but the core of the phospholipid bilayer itself is hydrophobic. And so consequently, some things can get in and some things cannot get into a cell. It's called a semi-permeable membrane. And a living cell membrane also has a lot of different kinds of proteins to facilitate diffusion and transport across the cell membrane. So in our example here, this is not a living cell membrane because it doesn't have any proteins in it, but it's that phospholipid bilayer, and we can use it as a good example. The phospholipid bilayer here is just kind of like a soap bubble with water on the inside and water on the outside. We're going to dissolve some salt, so let's just say we dissolve some salt in this beaker, and we'll find that the salt stays on the outside, but it just can't get on the inside of the membrane because the ions can't cross that hydrophobic barrier. And we got to make a solution. Let's say we're going to make 125 millimolar solution of sodium chloride. And so let's just talk briefly about how we're going to make that. And the answer is we first need to calculate the molecular weight of sodium chloride. And the molecular weight of any molecule is calculated in the same way. We simply add up the atomic masses of the atoms that make it up. So we go to the periodic table, and that lists the atomic masses, and we're going to round these numbers off, but the atomic mass of sodium is equal to 23. The atomic mass of chlorine is equal to 35. And to get the molecular weight, so-called molecular weight of sodium chloride, we just add them up, and so the molecular weight is 58. Okay, and we're going to want to keep that number, but let's just look at a couple more things since we're here. What about the molecular weight of water? Molecular weight of water is 1 oxygen at 16 and 2 hydrogens at 2, so the molecular weight of water equals 18. The molecular weight of methane, it's carbon, that's 12, and then 4 hydrogens. So methane is CH4, and that's molecular weight is 16. Here's one. Glucose has a molecular formula of C6H12O6, and we can add those up. 6 carbons at 12 each is 72. 12 hydrogens at 1 each is 12, and 6 oxygens at 16 each. Multiply those all together and add them up, and we get a molecular weight of 180 for glucose. So that's how you calculate the molecular weight of any molecule. Again, this is the number we want to run with, and so we take that number and we go back to, well, let's just go over here, and we will calculate the amount of grams we need to make 125 millimolar sodium chloride. And the way we do that is I always on paper say, okay, I'm going to make 1 liter, and I might not need a final liter. We'll calculate that, but let's start off, say on paper I make 1 liter, and that's great because 1 molar equals 1 mole per liter. And so if I want a 1 molar solution and I want 1 liter, I just want 1 mole of material. And mole is defined as the molecular weight of anything in grams. So 1 mole of sodium chloride is equal to 58 grams. We don't want a 1 molar solution, we want a 125 millimolar solution. And so we're just going to take that 58 grams. We don't need that much. We want a fraction of that much. And the amount we want is to multiply that times 125 millimolar over 1,000 millimolar. That's the same. 1,000 millimolar equals 1 molar. So we're just going to take 125 divided by 1,000 times 58, and we're going to get that is going to be equal to 7.25 grams. So to make 125 millimolar sodium chloride, we would take 7.25 grams and dissolve it up to 1 liter. Let's say if we were asked this question and we were first asked, oh, we need 2 liters. Well, we calculate how much we need for 1 liter, and then we just multiply it times the volume we really need. Okay, so we're going to do that. We're going to dissolve 7.2, well, let's say we made 2 liters, so 2 times 7.25 is 14.5. So let's say that we go back to our beaker and we dissolve 14.5 grams up to 2 liters, and we get a solution of 125 millimolar. So if we did that and we added that salt, the salt would dissolve throughout, diffuse throughout this beaker, and we could take a drop anywhere in this beaker, and the concentration in that drop would be 125 millimolar. We're not talking about a cell, we're just talking about this artificial membrane, and no salt will cross that artificial membrane. The salt is going to stay on the outside. The concentration on the outside is 125 millimolar, and there's what's called a concentration gradient. So going from the outside to the inside, we go from a high concentration to a low concentration, and biologists call that a concentration gradient. Gradient kind of like a hill. And the salt would like to flow downhill. It would like to diffuse into the cell because there's a higher concentration outside than inside. Imagine if we poked a little hole in there. The salt would start to diffuse inside. So let's just do that. Let's say we poke a little hole, and the salt will start to diffuse inside. And it'll start to diffuse inside, and it will continue to diffuse inside until the concentration of salt on the inside is the same. And at that point, the salt will continue to diffuse through this hole, but it will be diffusing in and out at the same rate, so that the net diffusion will be 0. And so that's what happens when we reach equilibrium. Same concentration inside, outside. And it's just passive diffusion, just the salt floating in through the hole like that to get to that. Okay, so now let's say we seal it up and we add some more salt. So let's say we add some more salt, and we bring the outside concentration up to 500 millimolar. So once again, we have this concentration gradient, and the salt would like to diffuse in. There's already a lot of salt in there, but more salt would like to diffuse in, and it would like to diffuse in until the concentration on the inside is the same on the outside. It can't diffuse in, and so what happens in this case? What happens in this case is this, that water can cross the membrane, and water is crossing the membrane. There's water leaking in and out of the membrane. But because there's more salt on the outside, water will diffuse out of the cell, out of this membrane-bound cell, faster. And as it diffuses out, the membrane is going to shrivel and get smaller. And as it gets smaller, the salt will start increasing in concentration on the inside. And that just happens just by diffusion of water leaving the cell, and as it leaves the cell, the salt concentration will increase. And water will be flowing in and out of the cell, but it will flow out of the cell at a higher rate, and so water's leaving the cell, and the cell will be shrinking. And the cell's going to shrink and shrink and shrink until it reaches equilibrium. And it will reach equilibrium when the concentration on the outside is equal to the concentration on the inside. And water is diffusing back and forth, and now at the same rate. Like that. Here's some different examples to show you some of the rules of osmosis. Here's one. It doesn't matter what's on the inside and outside. All that matters is the concentration. These concentrations are the same. The sugars can't diffuse across the membrane. Water's diffusing across the membrane, and water's diffusing across the membrane at an equal rate because the total concentration on the inside and outside is the same. This is said to be an isotonic solution. Here's a situation where, it's the same, but that doesn't matter at all. What matters is the total concentration on the inside and total concentration on the outside. In this case, there's a higher concentration on the outside, so water is going to diffuse out at a higher rate than in. And this solution is said to be hypertonic, salty on the outside, I know it's not salt, but I always think of it as salt. Then here's a situation where the concentration is higher on the inside than the outside. And in this case, what's going to happen is that water is going to diffuse in at a higher rate than out. And as it diffuses in, the cell membrane is going to swell. And as it swells, the volume gets bigger, the concentration of glucose will decrease. This is said to be a hypotonic solution. In a hypotonic solution, the cell swells. Here's another kind of example. We've got two things on the outside, one thing on the inside. Those don't matter. What matters is the total concentration. In this case, the total concentration is equal, so this is an isotonic solution. Concentration on the outside is the same as the concentration on the inside. Here's another example, a variety of different things on the outside. Add those all up, they're equal to the inside, and so this is also isotonic. That means water will diffuse in and out, but it'll diffuse in and out at the same rate, and there won't be any change in the size of the cell. The rule of just adding things up gives a value, and lots of times scientists will call that milliosmolar. Because it's a concentration not of any one substance, but of the total solute concentration, like that. And so in this case, 200 millimolar on the inside, 200 millimolar on the outside, isotonic. Here's an interesting example. We start out like this, where we have sucrose on the outside, glucose on the inside. That doesn't matter. This matters. They're equal, so it's isotonic. But this is interesting. Sucrose is actually glucose and fructose cooked together. So you have these two hooked together, and what happens if you split that? So if you split that, now you'll have 100 millimolar glucose plus 100 millimolar fructose on the outside, and you've got the same type of solution. You just split the molecule right here, and all of a sudden you've gone to a hypertonic solution. And that's really a curious aspect of osmolarity. It's kind of counterintuitive, I think, and but that's how osmosis works. We'll just look at these guys. These are from your book, and these are real cells. And in a hypotonic solution, cells like this blood cell will swell, because a hypotonic solution means low salt, low concentration of solids on the outside. So higher concentration inside, more water will diffuse in than out, and the cell will swell. It might even burst, and if it bursts, that's called lysis. Okay. Here is an example of a isotonic solution. Water's going in and out at the same rate. The cell's in equilibrium, and the cell shape and size doesn't change. And then lastly, if we have a high salt concentration on the outside, water is going to rush out of the cell, and less water is going to come in. The cell will shrivel. And those are just examples of real living cells and how the cell membrane performs in a living cell. And that's it for now.